All right, let's get started. Hi, everyone. Welcome to the next seminar. So I'm delighted to introduce to you today Anton Sokolov, who has recently been awarded his PhD from DESY. So he was a PhD student of Andreas Ringwald. And he's now, so he's now got his PhD and is moving to a position in Liverpool to work with Ed Hardy. So Anton has written this very interesting and potentially very important paper, I think, on electromagnetic couplings of axions. So I decided to invite him after watching his talk at a conference recently. So thank you for waking up very early to come and talk to us, Anton, and I'll leave it with you.
Okay, thank you very much for the invitation. Yes, and for this nice introduction. Indeed, I want to talk today about our papers with Andreas Ringwald, so our research, which is based on a recent article on Archive and also a published paper, which was published like a year and a half ago. This work is done in collaboration with Andreas Ringwald at the Deutsches Elektronensynchron DESY in Hamburg. Let me start. So here I just give an outline of the talk. So we will consider the following topics, just for you to know from the beginning what will be discussed. So we'll do first a small recap on axions, then discuss how axion electrodynamics coexists with electric magnetic duality symmetry, and what are the implications of this coexistence. Then we will discuss some peculiar theory of quantum electromagnetic dynamics. I will explain which is a bit different from normal quantum electrodynamics, and which we will take advantage of. Then we will discuss electromagnetic interactions of axions finally, and we will see that there can be some new couplings for axions interacting with photons, and I will give then the theoretical motivations for these new couplings and discuss some models some explicit UV-complete models where these couplings can arise. We will see that these couplings arise in models with heavy magnetic monopoles. And then I will discuss also phenomenology. So let me start. So why considering axions? So actually axions are very well-motivated candidates beyond the standard model physics because they can explain both mystery of lambda CDM model and of the present day cosmology and astrophysics, which is dark matter. And the relevant question here is what makes cold dark matter, and axions provide a very nice solution to this problem by a very simple mechanism, which is a normally misalignment mechanism or decay of axion of topological objects like axion strings. Then also axions were initially introduced to solve the problem of CP conservation in strong interactions. So actually the theory of strong interactions, QCD, predicts that there is some parameter theta in the theory, which could be any possible number in principle, but then our observations tell us that this theta parameter is super small. So actually it is directly proportional to the electric dipole moment of the neutron, and it turns out that this electric dipole moment is very, very small, and it couldn't be measured with a very precise experiments. And this means that this theta parameter is basically zero. and there is no reason for such a coincidence in QCD. So people thought of the Pichey-Quinn mechanism, which can explain this problem, and axions are the necessary ingredient of this Pichey-Quinn mechanism, and they can nicely dynamically drive this theta parameter to 0 in QCD. So these are probably the two major motivations for considering axions. There exist also other like astrophysical hints which point to the existence of some light particle, like axion-like particle, and some string theory motivations. So there exists really a lot of reasons to believe that axions solve many particle physics problems and arise in many theories. So now, as promised, let me come to the electromagnetic duality symmetry and explain what it has to do with axion electrodynamics. The three Maxwell equations written here, they are invariant under the SO2 rotations of electromagnetic fields. This is well known, but what is less known is how this comes about in the Lagrangian approach. So in the Lagrangian approach, the electromagnetic action is given by so this formula here, which is E squared minus H squared, and it seems that this Lagrangian actually breaks the electric-magnetic duality symmetry. So this combination is actually not symmetric with respect to SO2 rotations of electric and magnetic fields, and the resolution of this of this is that the electromagnetic action is actually not a function of electric and magnetic fields, but function of the potentials. And the relevant part of the potential here is the transverse part of the vector potential, so which is connected to electric and magnetic fields as follows, written here. And if we write now electromagnetic action in terms of the transverse part of the vector potential here, then we can see that it preserves SO2 invariance, and this invariance is also given by a very strange formula, which are written at the bottom of the slide, that the transformation of the vector potential, which corresponds to the electric-magnetic duality symmetry, is actually non-local. So you see here there is an inverse curl operator involved, and this operator is well defined because it acts on the transverse part of the vector potential, and you can check explicitly that this transformation changes the Lagrangian by only time derivative. So really the action remains unchanged. So now the question is, what if we introduce axions? So actually, we can see easily that when we introduce axion in a conventional way here, like axion times f of dual, or axion times electric times magnetic field in the Lagrangian, and we can see that varying over the four potential A mu, we derive the equations of motion, which actually break the electric-magnetic duality symmetry. So what happens is that here, if we now even simply exchange electric and magnetic fields in this equation, so we see that they are obviously not symmetric with respect to such an interchange, and really axion chooses, so this kind of coupling of axion to electromagnetic field chooses some particular direction in the electric magnetic plane and breaks the symmetry in a particular way. So, and the question is, which we asked, is whether this breaking can occur in some other way. So, can axion break electric magnetic symmetry in a different way? Yeah, so here also what is interesting is that the coupling GA gamma gamma here is given by this known expression where it is proportional to the electric charge squared divided by the axion decay constant, so some high energy. So this axion decay constant is proportional to some high energy H Queen scale, and here we have this famous structure E over n divided E divided over n, where E and n are anomaly coefficients, so they are whole numbers, which can have different values depending on the exact model which we consider. So there are two main families of models, KSVZ and DFZ axions, which yield slightly different E over n ratio. So yeah, so and in the end, the other question is, so if we now break the symmetry differently, so what will be the coupling? So this analog of GA gamma gamma, yeah, and what will be the models which provide such new couplings? So there are a lot of questions, and first let me illustrate with an example, so that you understand how, in principle, we can get these new couplings. I will not start with some complicated theory as we will do later, but just in a, so to say, naive approach, we can already see that such couplings can arise. Let us just change a viewpoint on the electrically charged particles of the standard model. So we know that in the standard model, all particles are electrically charged, but not magnetically charged. But really, there is a duality invariance of the free electromagnetic field. And this means that absolute directions in the electric magnetic plane have no physical meaning. So you could also say that all the particles in the standard model carry magnetic charge. And actually, because of this invariance, one can also think of standard models, or standard model particles, as so to say, magnetic monopoles of the dual potential. So if we introduce dual potential B in this way, so we say that now electric field is given by the curl of the vector potential, and the magnetic field is given so by this expression here, which is minus B dot minus the gradient of B0. So if we treat now electromagnetic fields in terms of this dual potential, then all electrically charged particles are now, although they have electric charge, but this electric charge arises, so to say, as a magnetic monopole from the B potential, and as because of the electric magnetic duality symmetry, this is completely valid picture, and one can now consider again the coupling of axion to electromagnetic. Yeah.
Can I ask you a question? About the duality. So this vector potential, which you call dual, it's dual in what sense? The usual, for example, the dual for the one form would be a three form, which carries no freedom.
Yeah, it's in the okay, in the context of electric-magnetic duality symmetry. So it's not dual in the sense of just mathematically like Hodge-star operator. It's dual in the sense that that we can rotate. In this electric-magnetic plane, we rotate electric field into magnetic field, say, and this action would rotate this A potential, so like normal potential, into the B potential. So actually, yeah, this dual for potential is just defined by these expressions here, that which connected to the electric and magnetic field. Yeah, so more or less, it means that so later I will show that if we write a theory in terms of A and B, so in terms of two potentials, then the rotation in the electric magnetic plane corresponds to the rotation in the AB plane. So this that's why I call it a dual for potential, and this is I think a conventional term for it.
Yeah, but they do not carry new degrees of freedom per se, right?
Yes, it does not carry any new degrees.
Okay.
So this is just an alternative description, so to say. So in this example, which I'm giving, I say, okay, we forget that there exists A potential, and we formulate electrodynamics in terms of B potential.
Okay.
So we just say from the beginning. And then what I'm saying is that if we introduce the potential in this way, then like normal particles will arise because of the singularities, like Dirac string type singularities of this B potential. And then, so to say, although they electrically charged, they are really magnetic monopoles of the dual potential. This is the idea. Yes, and then, so if we now consider again the axion coupling to electromagnetic fields, which is A F of dual here, or so A E times H, we see that actually we get a different equations of motion. And the reason is, although here the Lagrangian looks as if it has the same structure, especially so in terms of electric and magnetic fields, Lagrangian has the same structure as previously, but really Lagrangian and action is a functional of the potentials, not of the electric and magnetic fields. So when we derive equations of motion, we have to vary the action now with respect to this dual for potential, so the other potential. And when we vary with respect to the other for potential, we really get the other version of axion Maxwell equations. So for instance, here you see that so before we had divergence E proportional to some, so here divergence E proportional to some effective electric current, effective electric charge from the gradient of axion field. And here we don't have this term, but we now have a effective magnetic charge, so to say, from arising from the gradient of axion field here, because divergence of the magnetic field is not zero. And we have an effective, so instead of effective electric current, we now get effective magnetic current generated by the axion field. So actually we get different axion Maxwell equations and potentially different phenomenological implications. So now let me introduce, so we see that there exists some other coupling in principle, and also there is no reason for this J gamma gamma to be equal to the normal J gamma gamma expression which we had here. So really we could have something different. The next goal of the talk is first to develop in a systematic way all possible electromagnetic couplings. So we see that there can exist some other form of axion Maxwell equations. So the question is then, what is the most generic form of what is most general form of the axion-Maxwell equations and of the axion interactions with photons, and what are the values of this extra couplings, so of this new axion-photon couplings in other, so in UV complete series of which implement Pichet-Quinn mechanism. Okay, so but first let me start with with the conventional axion-photon Lagrangian. So again, here with the normal J gamma gamma coupling, and discuss that actually this coupling is very well constrained by many different experiments and astrophysical observations. So you see here, and the reason is that this one coupling actually governs a lot of different processes like axion-photon conversion, external magnetic fields, Primakov effect, which governs axion production in stars, and effects in helioskopes where axion induces extra magnetic field in a cavity. So there are really a lot of constraints, and here I show also some astrophysical hints and the parameter space region of the parameter space predicted by some popular axion models such as KSVZ and DFZ. So here you can see this band here, and so you can see that it is definitely worth to explore more theory of axions, because like these astrophysical hints, they point to completely different region of the parameter space than the theoretical models. And so also, so as we will see, we'll get the couplings which will be more possible to probe in the future experiments. So okay, so now we can ask the general question about this Lagrangian. So normally one wants to find, if one asks the question, what is the most general axion-photon Lagrangian consistent with the symmetries of which we have, which are the gauge invariance of electromagnetic fields, axion shift symmetry. So axion is actually the angular degree of freedom. So when we change by axion by 2 pi n times the Pichet-Quinn scale, we should the Lagrangian should remain invariant. So if we now take into account the symmetries, it seems that this Lagrangian is the only possible form for axion-photon Lagrangian. But really, maybe what we miss here can be understood from our discussion of the electric-magnetic duality symmetry. So really, we saw that the transformation of the potential which corresponds to the duality rotation is actually non-local, and so maybe what we lose is actually some non-local coupling of axion to the A potential, so which could give us other kind of axion-photon couplings, and also which could provide for this other different direction of the electric-magnetic duality symmetry breaking by axion fields. And here the locality of our Lagrangian selects one particular direction in the electric-magnetic plane. But again, so the non-locality in the Lagrangian does not mean that the physics and the effects will be non-local also. So, and here, one could probably proceed with non-local couplings, but it is more convenient to study, to consider the local theory, but which will implement this electric-magnetic duality symmetry in a like in a manifest way, where it will be given by some obvious rotation on the potentials. And such a theory exists. It is its Zwanziger theory. Here, let me adopt some simplified notations that introduce this wedge product sign for d mu a nu minus d nu a mu to write it more compactly. And also I will denote now the dual tensor with d letter in the upper right corner. And then we can consider the Zwanziger Lagrangian, which is written here, the kinetic term of it. So Zwanziger Lagrangian involves two four potentials, A mu and B mu. And so you can see that this Lagrangian is actually invariant with respect to the rotations in AB plane. So actually the first term, so the first two terms are even invariant with respect to any special linear transformation, not necessarily rotation. So the connection of these A and B's to normal electric and magnetic fields, or F and F dual tensors, is given here. And we see really that the rotation of F into F dual corresponds to the rotation of A into B. And what is strange about this Lagrangian is that it involves a fixed four vector, which is n mu here. And it seems that the theory violates Lorentz invariance then, but really it does not. And it turns out this four vector, it just it does not enter any physical observable. Let me discuss in a bit more detail. So the theory is called quantum electromagnetic dynamics, and it was formulated first by Schwinger and then by Zwanziger, but actually Schwinger formulated in a non-local fashion. So actually the Zwanziger approach is advantageous in a sense that Lagrangian is local, so we don't have any non-localities, and also we get this manifest electric magnetic duality symmetry, so rotation of in the AB plane. So what is important is that because of the peculiar form of the kinetic term, which I showed, we get two vector potentials, so two potentials, but we get only one particle, so which is a photon. So we don't get two photons, and it is not like a theory of which involves some dark photon. Also, we have two four potentials. They are not independent. So really, so there are constraints which connect one potential to the other. So this then the theory, as I mentioned already, is Lorentz invariant, although there is an extra vector n mu, and so the Lorentz invariance of the theory is most conveniently shown in the path integral approach. So you can show that the partition function is does not depend on n mu after you integrate over A and B fields in the path integral. And this was done by Zwanziger, Brandt, and Neri. What is also interesting is that the theory is generally not CP invariant. The theory is generally not CP invariant just because any theory of dyons can have CP violation. So this happens just because this A and B, they have different parity properties. So A is like normal 4 potential, and B is so has a opposite transformation with respect to parity. Yeah, then if we have dyons, if we have a current which couples to both A and B, then because they have different transformations with respect to CP, we get necessarily we can get CP violation in this theory. Yes. So okay, now maybe let me explain a bit more Zwanziger theory. So here now we have I write the total Lagrangian, which involves now electric and magnetic currents also. What this theory was really invented for in the beginning is to incorporate magnetically charged particles into the quantum field theory framework. So really, when Dirac in 1931 discovered quantum mechanical description of magnetic monopoles, he described them just in terms of one potential, and then as a just stationary sources of radial magnetic field. But then the question is, if we now want to do quantum field theory, we want to have quantum fields which can be charged magnetically, and for this we need to introduce something like this coupling. So we have to couple magnetic current to some vector to some 4 potential, and actually in the quantum field theory it turns out that the introduction of the second 4 potential is really necessary. So the Schwinger theory, which I mentioned, which is non-local, also involves second 4 potential. So because if you fully quantize these magnetically charged particles, you cannot get rid of it, basically. And then so Zwanziger also introduced the, so we can introduce the gauge fixing part. So we have now 2 gauge invariances of A and B separately. So for instance, we can fix it with this gauge fixing Lagrangian. And what is interesting is that then we will get equations of motion which factorize, so for which the differential operator factorizes. And we see that they are basically the first order differential equations. And this is, I think, a nice also illustration. So maybe intuitive, can give an intuitive understanding why 2 4 potentials describe one particle, which is a photon, and that basically what we have is a first order system, and instead of one equation for which would be second order differential equation, we get 2 first order differential equations. So actually we double the number of variables, but we have 2 equations instead of 1. Okay, and after we define properly this n times d inverse operator, so, or one can say we impose boundary conditions, we get just the normal Maxwell equations from these equations of motion. And now, so we consider this theory, and we asked what can be so what we developed an effective field theory approach to this quantum electromagnetic dynamics theory, and in this approach, so we classified all possible marginal operators consistent with the symmetries of quantum electromagnetic dynamics. And then we also wrote down all dimension 5 operators which involve axion, which are also consistent with the axion discrete shift symmetry, which I outlined earlier. And so the result is written here. So actually, when we write all, so we just consider all possible operators, we get 4 different axion interactions with photons possible here. So it is easy to understand. First 3 are just analogs of FF dual, but written where F and F dual, so to say, is written in terms of different potentials. So we can have dA dual, or we can have dB dual. So this is the coupling actually which we had in our simple example in the beginning. And we can also have dA dual. So this coupling is also possible. It's still so all this trace is still just a total derivative, and so axion still has a shift symmetry. But what is interesting about this dA dual coupling is that it is CP violating. So as I said, A and B have different CP transformation properties. So this coupling is CP violating, and this is interesting because in normal axion electrodynamics, the interaction is CP conserving. So we expect some extra effects associated with this coupling. And then there is a coupling which is a bit more difficult and theoretical. This is a Witten effect-induced axion-photon interaction, and actually this coupling has been discussed already in the literature, and it concerns the interactions of axions. So the vertex which consists of axion line, then line of the magnetic current, and the A for potential, and describes interactions of axion, electromagnetic interaction between axion and magnetic monopoles. So let me now stress that this effective field theory is valid for any axion or axion-like particle. So this also will be also true for axion-like particle. So we generalized the Witten effect-induced interaction, which is normally just written in terms of AF of dual term as usual. So we generalized it to the more general case where the magnetic charges can be dynamical, not necessarily just so to say, so to the case where the magnetic charges are now treated in full quantum field theory framework. Also what we see from this Witten effect-induced axion-photon interaction coupling here is that axion is actually not symmetric with respect to arbitrary shifts, and this means that this coupling would give some mass to the axion, so generate some potential for the axion. But we also see that really axions do not have to get this extra mass, because we can also consider just a theory without this Witten effect-induced axion-photon interaction. So if you consider just the first 3 axion-photon interactions, then we don't have this effect, and we don't have mass for axions arising from the magnetic monopoles. I think this is nice, because usually people just consider it in terms of AF of dual term, and then if you introduce AF of dual, then you automatically have to have the Witten effect coupling. And so, I mean, then from this one term, it seems that you automatically get both this coupling and this coupling, so both dA dual and the Witten effect induced coupling. So yeah, let me explain in a bit more detail this Witten effect induced axion-photon interaction. So first, how do we derive this coupling? Because for the first three, it is clear that this is just DA dual, so and DB dual, so all the combinations of the potentials, which are similar to what we had in normal electrodynamics. But here we also have some coefficient. You see E squared divided by 4 pi squared times the Pichekhin scale. So the question is now, which I will try to answer, how we got this coefficient and why this is really the Witten effect induced axion-photon interaction. First, we can start with the CP violation in quantum electromagnetic dynamics. So this is related because to get axion interaction with photons, or with magnetic monopoles, we can just introduce first the theta parameter into the theory, which is a CP violating parameter, and then exchange it for the axion field. So here we see that if there exists in quantum electromagnetic dynamics, if there exists a dyon with charges Qg, but no dyon with minus Qg charges, then we can solve the quantization condition and see that the electric charges of particles are really not quantized, but there can be some non-quantized contribution proportional to the parameter theta. Then we see also that this theta is an angular variable because here we have just integers, arbitrary integers. So shifts by 2 pi n do not affect the electric charge. So so introducing this electric charge into the Zwanzig-Lagrangian, so we see that the interaction part becomes like this. So now you have magnetic current times the magnetic Fock potential. But then due to the gauge invariance, theta cannot be promoted to a field because so actually we consider if theta varies, then actually the gauge transformation of A is not a symmetry of this Lagrangian, but we can save this by introducing an extra degree of freedom, which is like a Stuckelberg field, and this is really an instanton degree of freedom which lives on the magnetic monopole. And from this we understand that actually this kind of coupling arises in for the 12-Polyakov magnetic monopoles, which arise from the breaking, spontaneous breaking of the non-abelian gauge theory. And in non-abelian gauge theory we have an instanton, so we have instantons, and these instanton effects, they actually survive on the monopole, and they survive in a form of this extra pi degree of freedom, which is also known as dyon collective coordinate. Yeah, so we actually also automatically account for the Rubakov-Coulomb effect. So okay, due to this coupling of electric current to the phi degree of freedom. So now when we derive equations of motion from the Lagrangian, from the general Lagrangian which I showed, we get this kind of axion-Maxwell equations, and we can rewrite them in terms of the electric and magnetic fields. And now we really see that we get a lot of new terms compared to the normal axion-Maxwell equations. Yeah, actually this Witten effect induced coupling, which I discussed before, it does not enter here because of course, for it to be important, we have to have some magnetic current, which is 0 in the laboratory. normally because we haven't found magnetic monopoles, so no, we cannot use them.
Can I ask a question, Anton?
Yes, yes.
Yeah, that's interesting, this Witten effect. But if it could be a surface term, like it is in electrical engineering, when they have an external input of energy, they model it with magnetic current boundary source. So I believe it comes in there because that's related to the Witten effect if you bring in surface terms.
Yes, so in principle it is possible. Yeah, so so this magnetic current can be an effective magnetic current in some condensed matter systems, say, or so in principle, yeah. So probably this magnetic current.
I believe it exists.
Fundamental. Yeah.
It's a fictitious magnetic currents do exist in a lot of physical systems, just like fictitious electrical currents. And it's like an emergent theory which is describing a more some sort of something happening on the microscopic scale, but this is just an average macroscopic theory. That's all I would like to say. Yeah.
Okay. Yeah. Thank you for this comment. So yeah, really. So we actually did not consider this coupling then because we just didn't consider this effective, that there can be some effective magnetic currents in the medium, but in principle this is possible. So now let me give brief theoretical motivation for these new couplings. So we'll introduce some new UV complete axion models which yield these new couplings which are GABB and GAAB. So the CP violating coupling and CP conserving, so to say CP conserving coupling from DB dual term in the Lagrangian. So I will explain why these models are theoretically well motivated, and we will calculate these couplings and see how they compare to the conventional axion-photon coupling. So we will see that all these models which yield new couplings, they are actually introduce heavy magnetic monopoles. So now let me outline the motivation for the existence of magnetic monopoles. Really, magnetic monopoles solve, first of all, problem of the standard model, or some very puzzling observation in the standard model, that the electric charges of electron and proton are exactly opposite to each other. So the absolute values of the electric charges of electron and proton are the same. And this cannot be explained in the standard model itself. But if one involves magnetic monopoles, then, as it was shown by derive, all electric charges have to be proportional to the elementary electric charge, say electric charge of the electron, and then the quantization condition, which was derived by Dirac, explains this quantization of charge question of the standard model. And then magnetic monopoles arise naturally in grant unified theories, and so in many constructions where you can have some unifying gauge group and some unification of forces, and even more interestingly, so magnetic monopoles arise in any consistent quantum gravity theory. So with quantized charges, which means with charges as absorbed in nature. This was found, for instance, this was explained nicely by Banks and Seiberg. So Palczynski said that existence of magnetic monopoles seems like one of the safest bets that one can make about physics not yet seen. And this is also so connected to this quantization of charge problem, and also to the fact that in any consistent quantum gravity theory, it seems that monopoles have to arise. So like in string theory, and but the problem is then, although there are so good theoretical motivations for considering magnetic monopoles, their mass is not known, and many models predict very, very heavy magnetic monopoles. And this means that we cannot probe magnetic monopoles, so with the energies which we have in our experiments, accessible to our experiments. And the solution is maybe to look for the indirect effects of magnetic monopoles. And this is what, as we will see, axion-photon interactions can provide us with. So it turns out that these heavy magnetic monopoles, so normally such effects, so indirect effects, will be suppressed by the monopole mass. But in axion physics, so we already have suppression by the Pichaikin scale. And this means that if we now have also suppression by, so as we will see, the magnetic monopole mass in these models will be associated to the Pichaikin scale. And then if these are like the same scale, then with axion physics, we can probe magnetic monopoles. So this is the idea. So now let me discuss the theoretic, so some UV complete models of this, which can yield new axion-photon couplings. So first, let me review how this coupling arises in conventional models like KSVZ and DFSZ-like models. So it always arises from the interaction of axion with some heavy fermions psi, which are charged under the electromagnetic interaction. So here you see that, so we have to consider this triangular diagram, and actually in the limit where the mass of this particle is very large, this diagram is just given by the anomaly. And from Adler-Bardeen theorem, we know that anomaly does not receive any high order corrections in E. So actually, this is a non-perturbative result. And we can say, so calculating this diagram, we see that G gamma gamma coupling is E squared divided by the axion decay constant. But but we introduce new heavy particles in KSVZ models which carry some electric charges. So why not we introduce also a magnetic charge for this particle? So if we introduce a magnetic charge for this particle, actually the calculation is not changed. And although it is now non-perturbative, and so you can do this calculation in strictly in the Zwanziger formalism, which I described before, and you can see that actually due to the fact that this calculation is non-perturbative, you still get the result. So even without perturbation theory, so this is probably the only thing which can be reliably calculated within this Zwanziger framework, because normally Zwanziger theory is of course non-perturbative due to the large value of the magnetic charge, and so you cannot calculate anything in perturbation theory. But again, because this diagram is just given by the anomaly, you just get the coupling which is proportional to the magnetic charge squared now. And this is an exact calculation, so to say, when you send the mass of this heavy particle to infinity. And this is really justified because the mass of this particle is of order of the Pichaikin scale or axion decay constant, and this is normally a very, very large energy scale. So now let us introduce magnetic anomaly coefficients here. So by analogy with the electromagnetic anomaly coefficients, we can introduce just magnetic anomaly coefficients, which will be proportional to the magnetic charge squared. And then if we perform just a simple comparison of the normal J gamma gamma coupling and the new J gamma gamma coupling, which is proportional to G squared, so we see that they are ratio is proportional to G squared divided by E squared. And because of the large, so because the magnetic charge is very large and the electric charge is small, we get a huge enhancement of the coupling by 5 orders of magnitude, and potentially even more depending on the magnetic charge. So on the value of the magnetic charge, Z here. So here I show the comparison plot. So you see that really now the lines which correspond to this case with Z-like models, but with the magnetic charge running into the loop, they yield axion-photon couplings, which are much larger and much closer to the values predicted by astrophysical hints and to the values which can be probed by astrophysical observations or by future experiments. So one has to also note that in the strong sector, the model is analogous to case with Z. So we modify only the electromagnetic sector for this kind of models. And this means that we get the same cold dark matter abundance. So it also means that, so we can have axion dark matter, which will be easier to find with future experiments. And we get the same EDM coupling, the dipole moment coupling. So now let us consider this CP violating coupling, which, as I already said, the CP violation arises from the presence of dyons in the theory. So if we now consider this extra heavy fermion to be a dyon, then we get AB coupling, axion AB coupling, which is proportional to E times G. So because here, you now have both charges in the vertices. So one of the contributions will be proportional to E times G, and you can introduce so the dyon anomaly coefficient. So I'm sorry, here there should be dyon instead of magnetic, or so mixed electric magnetic anomaly coefficients, which are proportional to the product of electric and magnetic charges of these heavy dyons.
So,
and what is it? Yes.
In terms of effective operator, this is F squared term, AF squared.
Yes. So this is actually but again, so what one can what here one has to
I understand
that this is so this in the Maxwell equations it will be like F squared term, and the effects will be analogous to say to the dilaton coupling to F squared. Yes.
Okay.
So to say. But really, so this is
I understand in terms of
not really F squared in the Lagrangian. Yes. Okay. Yes, and what is interesting is that so now we get CP violating axion-photon couplings, and this CP violation is transferred from heavy dyons, and so we can really probe. So if we detect CP violating axion-photon interactions, say by means of electric dipole moments of electrons, say, or some other CP violating probes, so then we can say that there exist heavy dyons. So so we can get some information about the spectrum of heavy particles carrying both electric and magnetic charge. So now, let me also discuss one thing which I think is important to discuss. So one could say that our results are in apparent contradiction with previous claims in the literature. So by Agrawal and others, that so actually they had some papers where they claim that the main contribution to the axion-photon coupling is necessarily quantized in some units proportional to the electric charge squared. And so their argument is a bit theoretical, but it also it relies on the Witten effect induced axion-photon coupling. And so basically the idea is that so here, if you consider a FF dual in the normal formalism, then you shift the axion field. What you get is that the axion-photon coupling is like this electromagnetic anomaly coefficient divided by the domain wall number times this E squared, so times, say, the normal contribution to the coupling. This means that the axion-photon coupling is quantized in units of units proportional to the electric charge squared. And really, this argument takes advantage of the Witten effect that the term theta f of dual in normal electrodynamics is physically relevant. So normally we say that f of dual is a total derivative, so this term is not physically relevant. But if there exists magnetic monopoles, or if we have some non-trivial topology, then actually this term is relevant, and so one can introduce it into the action to account for the Witten effect. Yeah, but the problem is that oh, no problem, not a problem, but actually there is no contradiction, because what these authors do is they identify the two structures here, so theta f of dual here, which corresponds to the Witten effect, and a f of dual here, which corresponds to the axion-photon interaction. This is perfectly okay within the U1 gauge theory, so theory of electrodynamics. But what is important is that in such a formalism, the magnetic monopoles are not treated fully dynamically. So actually, this formalism cannot account, say, for the effects of loop of magnetic monopoles, because magnetic monopoles are not introduced as quantum fields in this description. So in no in no way can they be described as some quantum fields. Yeah, so, and actually more general formalism which we use, so say Zwanziger formalism or any formalism where magnetic monopoles can be treated as quantum fields, we can see that actually there is a coupling which corresponds to the Witten effect, so which I discussed and which is written here. But there are also other couplings, and really, the Witten effect coupling is not the only coupling, and although the Witten effect coupling is quantized as it was found before, actually the other couplings need not be quantized in terms of E squared, and so they can be also proportional to G squared. And so yeah, this is the explanation. And now, okay, let me now briefly discuss phenomenology. Due to the quantization condition, ABB coupling is much larger than AB coupling, and AB coupling is much larger than AA coupling. So again, because AA is proportional to the electric charge squared, AB to the electric times magnetic charge, and BB to the magnetic charge squared. So magnetic charge is much larger than electric charge. So this BB coupling is actually dominant. Now if we write the axion-Maxwell equations, so here I underlined the dominant terms. So most dominant terms are the BB coupling, and second dominant terms are AB coupling. And then if we, so here it is written in terms of the electric and magnetic fields, and you see that the conventional coupling, which is AA, is actually the least important coupling here. And this means that you really get some you can get some. So to say, we will be sensitive dominantly to these BB and AB couplings. But in many cases, it turns out actually that the whole effect of these new electrodynamics equations are to exchange AA coupling with BB coupling in the expressions. And this happens because for many effects where axions disappear or axions are produced, we can use axion equation of motion, say, to describe physics. And then we see that AA and BB couplings, they enter the equations symmetrically. And so, and BB coupling is the dominant one. So really, because of the symmetry, we can calculate all the probabilities for this process just by exchanging in the conventional expressions AA coupling with the BB coupling. And this would be, so the only effect will be enhancement of the interaction, not really some new qualitative result. So this also means that in the for the BB coupling, the constraints from high mass axion gyroscopes, so gyroscopes which probe high mass axions, and astrophysics, which also normally discusses these kinds of processes like Primakov effect or conversion external magnetic field. So the constraints will be the same. And where the constraints will not be the same are gyroscope experiments for low mass axion dark matter. So in this case, actually, considering the equations, you can see that we will, instead of having a dominance of the axion-induced magnetic field, we will have the dominant contribution of axion-induced electric field. So actually, just because we have magnetic current instead of the electric current from axions, yeah, we will have instead of the axion-induced magnetic field, we will have axion-induced electric field. But most of the yeah, I think almost all experiments which probe low mass axions, they actually probe the magnetic field. So they have magnetometers installed, and so yeah, it means that they are not really sensitive to these BB couplings. And this could mean that yeah, that maybe by measuring instead axion-induced electric field, we could, or some other different modes in our cavity, we could explore also the BB couplings. And if we, it also means that if we detect this BB coupling, then we can really qualitatively distinguish it from the AA coupling and say that so if we detect electric field instead of the magnetic field, then we can say that there really should exist magnetic monopoles. And so this would be an indirect probe of magnetic monopoles, which I advertised earlier in the talk. In the end, let me just mention that in light shining through wall experiments, we can actually probe also the AB coupling, because we have now control over the initial polarization of the photon. And as you see, BB coupling couples to the same, has the same combination of electric and magnetic fields as the conventional AA coupling. So it will also be sensitive only to the photon which is transverse to the which is along. So a photon which polarization of which is directed along the external magnetic field, but not to the photon with perpendicular polarization. But now AB coupling also can give us contribution from the photon which is polarized perpendicular to the magnetic field. So this is interesting. So if we say detect the dominant BB contribution and then we perform more sensitive light chains for wall experiments, we can also probe AB coupling and the CP violation. So yeah, it can be summarized on this plot here. And so here I show these BB, AB couplings in different models. So that's why we have quite a few lines and some bands. So we can populate all the parameter region here actually now. And you see that like axion dark matter could be easier to detect, as I said. And UPS2, which will be starting this year probably, is sensitive to the QCD axion, which is nice in these models. And we can see that also we don't put these projections from Abra, say, or other haloscope experiments, because as I thought, this would lead to qualitatively different physics. So this new coupling. So we actually cannot. So if we now perform some experiments which will be sensitive to the other, like to the electric fields, say the cavity X-induced electric fields, then we can probe these new couplings. So here in red, I show also the region which is corresponds to the axion dark matter, which has initial misalignment angle, which is not too small. So the principle of this region is also favored from the dark matter considerations. Okay. So yeah, let me skip this. And yeah, so let me come to the conclusions. So we found that heavy magnetic monopoles can influence low energy physics in an interesting way through axion-photon couplings. And yeah, we found new axion-photon couplings in the effective field theory approach, and we found some UV complete models featuring these couplings. Then yeah, we discussed unique signatures in haloscope experiments and that axion-photon interaction can violate CP. So, and we clarified some issues within axion theory. So I think this is the end. Thank you for your attention. I'm open for questions. Thank you.
Thank you, Anton. Yeah, very interesting talk. We've already had some discussion, but maybe we can have a few more quick questions. I see Mike has his hand up. Do you want to go first, Mike?
Yeah, so I'm interested in what you think about the electric vector potential, which is in your theory, because the difference between electric and magnetic potential, well, the electric field does work where the magnetic field doesn't. So there's a difference between electric vector potential and a magnetic vector potential is quite different physics. It's like an EDMs. I think it's like EDMs are not as prevalent in physics as the a magnetic dipole. I think it's related. Do you have any comments?
So what is your question? Is like
the question is what does it mean to have an electric vector potential? What do you think it means?
Yes. So
because I thought about this a lot.
I think that so here, yeah, we have. So why we have essentially this extra potential in our theory, this electric vector potential, is because in our UV complete models we have magnetic monopoles running in a loop, and so and from the perspective of magnetic monopoles, if we now introduce magnetic monopoles, then so to say, now to the opposite, like magnetic field does work, say, on this magnetic monopole. So as you're saying, so really I agree. So that if we have only electrically charged particles, then we don't need this second potential in principle. But if we have now magnetic charges, or so fundamental like now theories, or as you mentioned in some in medium, some effective magnetic currents, fictitious magnetic currents, then yeah, so the other potential becomes useful. And I think,
because it's when we have an EM, the integral around the closed path of the electric field is non-zero, and that's what you need to have an electric vector potential, and that's what you have in a non-conservative system. So as in the classical point of view. Anyway, that's it. I'll give someone else a chance to ask a question.
Okay, thank you for the question.
Anyone else?
Can I ask a question? Anton, thank you for a very nice talk. It was very interesting. So you mentioned, the monopoles typically also contribute, you mentioned that to the mass of the axion.
Yes.
Now, what I presumably miss, what is the contribution? I mean, does it spoil the CP, the strong CP solution, or?
No, so, but actually, so, yeah, I understand. So this was found not by us, but by some other people before us. So actually, this does not spoil the solution to the strong CP problem. And so this mass arises from this term here, where axion times magnetic current times the vector potential times the four potential. And the reason why this mass arises can be seen just because this term is not symmetric with respect to arbitrary shifts of axions.
Yeah.
But also from this, from here, we see that this mass arises only in a okay, so
yeah,
this mass arises when we have monopoles. So say in the medium of monopoles, if we have like, so that's why say in the early universe, if we have magnetic monopoles there, say they can induce some mass for the axion.
So we are not talking about the virtual monopoles here. You're talking about
in principle. Well, okay, so there was also an article which said that the virtual monopoles can contribute to the mass here by Matt Rees and others. But yeah, so yeah, I think virtual also can do it via this coupling. But then
why I'm asking this, because in principle you can think about the different monopoles as well, not just magnetic, but chromomagnetic monopoles in the low energy description of UCD, and there the situation would be different, right? So I assume that this is suppressed quite a bit, with one of a VA and the E squared, right?
Yes. Yes, so I think, yeah, probably it is additionally. So if we consider visual monopoles, then this effect is additionally suppressed even more than VA. Yes, but yeah, so you can look into calculations. So by saying Matt Rees and others, so I think they have this article like axion mass from monopoles or something like this, and there they derive expression for the.
Yeah. Usually it's known that if you look at for example, theta dependence of QCD vacuum in the presence of monopoles, there is the monopole loops which contribute to theta dependence. So I would assume that it would also contribute to the effective potential, obviously, right? Just QCD monopoles, which are kind of supposedly through the dual Higgs mechanism responsible for the confinement.
Yeah, so yeah, I never thought about chromomagnetic monopoles so for this coupling actually. Yeah, so in this context, although, so yeah, I skipped the part, but we also considered this the possibility that these heavy monopoles which we have running in the loop, they also have chromomagnetic charge. So in principle, this we considered, but not this kind of coupling. And yeah, so maybe it is possible, but the problem is that so in QCD it's more difficult because there does not exist like a Zwanziger or some description of QCD which would contain 4 potentials. So yeah, so and there does not exist, I think, even the analog of duality symmetry in non-abelian gauge theory. So somehow this
but the Witten effect will still exist, right?
Yes, Witten effect
and
will,
so on, right? With the theta parameter and so on. So
yes,
but
yes,
that's essential in your case, right? Beyond the description, the theoretical description.
Yes. So
okay. One more question. I'm sorry. You mentioned, of course, the ground unified theories so can you imagine this situation where this Zwanziger Lagrangian is a large distance approximation of this ground unified monopoles or non-abelian general polar monopoles?
So this Zwanziger Lagrangian, or in principle Schwinger Lagrangian, so this is just a low energy theory of any magnetic monopole, so any magnetic charges. So it applies also to like Topf-Polyakov monopoles, to the ground unified theories. So then, yeah, so the interesting thing would be maybe to find some ground unified theory or some model where monopoles arise like from symmetry breaking, so which will yield this kind of axion couplings. But
because in ground unified theories you have this common theta, which comes from the SU5 non-abelian, which kind of goes with each of the the broken standard model group. So it's quite non-trivial there, this theta term by itself. And on top of that, you have a monopoles in essence.
Yes, right? So here is, but in ground, so the additional complication is that we need, so in simplest models of Topf-Polyakov monopoles, say, these monopoles do not have spin. So, and we have to have fermionic monopoles. So for instance, so there are some complications, but in principle, maybe it's possible to construct such a model. But yeah, so we treated it as an effective field theory. Yes, in principle, it could be possible.
Anyone else? So maybe I can ask one final quick question. It's more of I guess more of a comment. There's another constraint, another astrophysical constraint, which is quite strong actually. It lies a little bit above in mass from the TeV transparency hint, and it's this the polarization of photons from magnetic white dwarfs. So the idea that you have the thermal photons emitted by the magnetic white dwarf, some of them converting into axions, leaving a residual polarization. I feel like that could be quite interesting here for your different couplings, because you have this, your GAA and your GBB, but then you also have this E squared minus B squared term with the GAB, with this interesting polarization dependence. So I wonder if that could be interesting for you. Have you come across this constraint? It's a fairly recent one.
Yes, so I heard about this. So I unfortunately haven't put it on the plot here, but yeah, so it's also interesting because it apparently closes this almost fully, I think, this transparency hint. So it's interesting, and I think, but concerning the polarization, I think it will still, so this constraint still will be valid for this theories, because polarization, effects from the dominant BB coupling as to the polarization are the same as from AA coupling, and in this regard, like so the dominant effect on the polarization will be so qualitatively the same.
Right.
So so this.
Could you go back to the other plot, the one after this one, where you had the different bands for your different couplings? Okay. So your AB, the AB is the dashed blue line.
Yes. So AB is suppressed. So although AB would yield some different results in polarization probes.
Okay. Well, thank you. You're right. So we had lots of nice discussion. So if anyone has any final questions, just shout out. But if not, I think we can give Anton a break and finish there.